Pressure. What is the mechanism for measuring pressure? Let's talk about air pressure. We talk about atmospheric pressure, don't we? You see, you know, when you go down into water, you experience the pressure on you because there is a column of water standing on you. And that column of water standing on you will be pressing on you, telling you, how dare you come and take my place? I'm supposed to belong there. It'll be pressing on you. And the deeper you go, harder will be the pressing on you. The deeper you go, the pressure will be greater. In the same way, we live in an ocean of air. The atmosphere is an ocean of air, and we are at the bottom of that ocean. There is large amount of air standing on top of you. It is pressing down on you. It's pressing you from everywhere. The atmosphere is applying pressure on you from everywhere. Why? It tells you, now look, the space you are occupying is mine. I want it. Get away. It's pressing you. Ever since you were born, you have been subjected to this continuous atmospheric pressure. Pressure exerted by the atmosphere from all sides. Air is a fluid and it exerts pressure in all directions. The pressure exerted by air is called the atmospheric pressure. It is a very important indicator for us. It indicates, in fact, it gives you a lot of indications about the weather patterns, the atmospheric pressure. The pressure exerted by atmosphere can be measured by a simple barometer. The instrument used for measuring atmospheric pressure is called a barometer. And you can use a glass tube and a certain amount of mercury to construct a barometer. Alright, let's see how one can be constructed. What all you need to do is take a long glass tube. Well, that glass tube has to be closed at one end and open at the other. A simple mercury barometer was constructed by an Italian physicist, Torricelli. Now what he did, he took a very long tube, not like this. This is a very small tube. He took a very long tube about a meter long, about a meter tall, closed at one end and opened at the other, and filled it with mercury. Well, I have filled it with water. Alright, I just want to explain the principle. I won't be able to make one. Now, then what he did, he closed this open end with his thumb like this and inverted it into a dish of mercury. Here, this is a dish of water like this. And now, what he noticed is, can you see here, there is a column of water standing here. Can you see that? There's a column of water standing there. Now, what is it that makes that column of water stand there? Well, there is something that is supporting it there. What is that something that's supported there? You know that the pressure exerted at any point on the same horizontal surface is the same. Is that right? Now, if you take points on the surface of water, what is the pressure on the surface of water? The pressure at any point on the surface of this water is the atmospheric pressure. And what is the pressure at any point at the same level inside the tube? It is the pressure exerted by this column of water. Now, therefore, is it reasonable for us to say that the pressure outside, which is atmospheric pressure, is equal to the pressure exerted by this column of water? Well, in this case, this is a mock example. This is not the real thing. Is that right? If the real thing, the water will not fall at all from here. Okay, let's now take a look at what Torricelli did. Now, I need to close it before taking out, otherwise the water will overflow here. Okay, let's see what Torricelli. Well, this is the arrangement, the experimental arrangement used by Torricelli. He took a very long tube, closed at one end and opened at the other, filled it with mercury, then closed the open end with the thumb, inverted the tube and inserted it into a dish of mercury. And what is the observation? What is the observation here? He found that a column of mercury was standing inside the tube, and he tested the space above it. It was found to be a vacuum. How do you explain the column of mercury standing in the tube? Now, he noticed that whenever he did this experiment, the length of the air column or the height of the mercury that is standing in the tube is about 760 millimeters when the experiment is done at sea level. It doesn't change. Well, what does that mean? The space above the mercury in there is a vacuum. Now, what does that mean? We talked about this. Now, why doesn't the column of mercury in the tube fall further? Why doesn't it fall further? If you can explain that to me using the example I showed you. Now, consider points A and B. This is point A and this is point B. Now, the point A is outside that tube, point B is inside the tube. And you notice that A and B are on the same horizontal surface. It means the pressure at A equal to the pressure at B. Is that right? Okay, so the pressure at A is the atmospheric pressure. Pressure at A is due to the air, due to the big column of air standing on top of it. And pressure at B, because there is no air above the mercury, pressure at B is purely due to the weight of mercury standing on it. So what conclusion can we take? Pressure at B is the pressure exerted by the 760 millimeters of mercury. Is it reasonable for us to conclude that pressure at A therefore should also be the same as the pressure exerted by 760 millimeters of mercury? Now, what does that mean? It means if I now hold my two hands like this, and on my left hand I have this big column of atmosphere. On my right hand I have a column of mercury 760 millimeters high. The pressure exerted by the column of mercury 760 millimeter high will be exactly equal to the pressure exerted by this very large column of air. And so we can therefore conveniently say, we can conveniently conclude that atmospheric pressure equal to the pressure exerted by the column of mercury in the tube. Once you can measure the height of the column of mercury in the tube, you can say the pressure exerted by this column of mercury is the same as the pressure exerted by the atmosphere anywhere on the surface wherever this experiment is done. Is that right? So pressure exerted by the atmosphere at sea level is approximately equivalent to the pressure exerted by 760 millimeters of mercury. Now, pressure exerted by 1 millimeter of mercury is called 1 torr. So, you can now use a unit for measuring atmospheric pressure. Pressure exerted by 1 millimeter of mercury is 1 torr. And how much is the atmospheric pressure? Atmospheric pressure is equivalent to the pressure exerted by 760 millimeters of mercury. So, atmospheric pressure is how many torr? Atmospheric pressure is 760 torr. Alright? Now, 1 torr, there's another unit for measuring pressure. 1 torr is 13.3 millibars. This is a commonly used unit for measuring pressure. A millibar. Look at the way we write it, small m, small b. 1 torr, the pressure exerted by 1 millimeter of mercury is 13.3 millibars. And therefore, 1 atmosphere, the pressure exerted by the atmosphere is 13.3 millibars multiplied by 760 millimeter, that is 1011 millibars. When we say the pressure of 1 atmosphere, we mean a pressure of 1011 millibars. Well, we are not familiar with measuring pressure in torr or millibars. What is the unit for pressure that we use as physicists? It's the Pascal, isn't it? So we need to figure out 1 atmosphere, which is 1011 millibars, is how many pascals? Alright, let's do that. Atmospheric pressure in absolute unit. Pascal is the absolute unit for